Okay, hi, welcome back. We're going to continue our Laplace transforms. Okay, so last video we actually reduced this Laplace transform into some partial fractions, and those partial fractions are relatively okay to inverse Laplace transform. We can see this one over here will just reduce to some exponential e to the minus t. These two over here, these are constants, b and c, if with respect to omega. If omega is a constant, b and c will be constant, and then you will have just some Laplace transform of this is actually a Laplace transform of sine and cosine. So you'll see there's just sine and cosine wave there, nothing too out of the blue. Okay, so nothing too out of the blue. These are sine and cosine waves. The only thing is that how do you inverse Laplace transform this? 1 over s plus 1 squared, because 1 over s plus 1 is a e to the minus t. If you can take a look back, we actually derived that. Then how are you going to do this? Okay, so I want to introduce something called frequency shift, and yeah, I won't introduce all the inverse Laplace transforms now, or Laplace transform properties, but as things go along and we might deal with complicated problems, then we'll start looking at different theorems. Okay, one of the Laplace transform properties is called frequency shift. So what does frequency shift have to do? Okay, so let's take a Laplace transform of exponential e to the minus at and some random function f of t. Okay, I say again, Laplace transform of e to the minus at times f of t. Okay, what will the Laplace transform be? So you just take the integral e to the minus at, ft, and e to the st. So let me comment this first. Yeah, I'll hide that for the time being. So e to the minus at, e to the st, right? And what happens? Okay, we can just combine these two together. A and s we can combine together here. And I want you to compare this with the original Laplace transform definition. Okay, compare this with the original Laplace transform definition. So look at Laplace transform of f of t. Okay, Laplace transform of f of t is 0, integrate from 0 to infinity, f of t e to the minus st dt. Now you notice that these two are almost identical except for the plus a here. Alright, again I say these two are almost identical except for the plus a here. So you can sort of think of it this way, right? If this Laplace transform is called f of s, this Laplace transform is called f of s. Okay, so I guess you can think of it this way. Everywhere you see s, replace it by s plus a, right? Okay, I say again. Everywhere you see s here, you just replace it with s plus a. So we can say, basically, when you have this thing, when you have this exponential, okay, when you have this exponential thing here, Laplace transform of e to the minus at ft is equals to this Laplace transform here, and this looks exactly identical to this, except everywhere you see s here, you just replace this whole thing with s plus a. Okay, so let me give you one example. Okay, so let's say we have you want to take Laplace transform of t squared, right? Okay, so mathcal L t squared. T squared. So what will be this Laplace transform? Okay, this Laplace transform I think we saw before. Okay, it's actually 2 over s cubed. Okay, so this Laplace transform is 2 over s cubed. So the frequency shift property is very simple. Okay, so if we were to do some exponential, for example, minus at, right? Let's do an exponential minus at, right? Laplace transform of this. So what's happened? How do we do this? So everywhere we see s here, we just replace it by s plus a. So okay, you can look at this. When we multiply e to the minus at to ft, okay, everywhere we see s in the original thing here, we will have s plus a. So of course for the other case, if you have e to the at, so we'll have s minus a. So this is called frequency shift. So if you want to shift your Laplace transforms left or right, you just multiply by exponential at. And I think you can see where this is going. Now, back to the question. How do we inverse Laplace? Okay, so back to the question. Okay, how do we inverse Laplace this term here? Okay, how do we inverse Laplace this? Okay, so I want you to note something. Again, we are going to take Laplace transform of t. Laplace transform of t is just 1 over s squared. Right? It's just 1 over s squared. Right? So Laplace transform of t is 1 over s squared. You can double check that in the tables and all, but this is the Laplace transform of t. Good. Okay, Laplace transform of t is 1 over s squared. Now, if you notice if you want s plus 1 at the bottom, right? S plus 1 at the bottom. So what do? Okay. So instead of 1 over s squared, you want 1 over s plus 1 squared. So what do? Just the only thing you need to do is just have a e to the minus at here, and that will give. And everywhere you have this s squared or s, you just have 1 over s plus 1 squared. And this is basically how you do the inverse Laplace of 1 over s plus 1 squared. Okay, so we inverse Laplace both sides. And then basically Laplace inverse minus 1 of this fraction. Okay? Left and right. Okay, and that's better. Okay, so now we found our inverse Laplace transform using this thing called frequency shift properties. Okay, let's see. Yeah, so this is how frequency shift properties come about. Is that you basically I'm not going to do thorough what do you call that derivation, but basically you can just inspect this Laplace transform and this Laplace transform. You'll see that they are almost similar except for this plus a. So everywhere, what you do is that you just substitute s with s plus a, and then everywhere you see s, you just replace it by s plus a. That's a very simple thing. So now we know that this 1 over s plus 1 squared is just a t times e to the minus at. Okay? Alright, so this part is more or less settled. And of course, that also means that these two parts are also more or less settled. So let's again see the y of t. Okay, let's see the y of t. Okay, y of t here. Okay, back to main question. Okay, let's take a look at y of t again. We have 2 plus s, okay, in this one. So what can we do? Let's break up the 2 plus s over here over s squared plus 1. Make our life a bit easier. Okay, so what is this equals to? Okay, well, we can do this s plus 1 over s, or s plus 1 squared. Sorry, s plus 1 squared. Alright, so now you have this. Then what do? Then we'll just have 1 over s plus 1. This is an exponential plus 1 over s squared plus, or s plus 1 squared. Okay, so not too difficult this to deal with this. All right, so let's put all of this together, and we'll just inverse Laplace all of this. I'm not going to write the final forms. I'll just leave it in A, B, C, D, and E, you know, kind of thing. Yeah. So let's do this. So we will just get this part. Yeah. Okay, we'll get this part. Okay, we'll inverse Laplace transform that. This thing we will just rewrite it as what we just derived. Okay, yt equals to 0 will come outside. Then I'll just bracket this. So 1 plus 1 over s plus 1. And now I think we are more or less ready to inverse Laplace everything. Okay, so maybe I'll do a left and right bracket just to make it look very neat. There we go. And let's do left or right over here and left. Okay, so much neater. Okay, so what can we do? I will just inverse Laplace all of these things here first, the initial conditions or boundary conditions, so that we have some analytical solution. Then we'll take out the I will just these two I will just inverse Laplace straight away. So this what was this? This was TE minus T, right? Okay, T e to the minus AT, or A in this case is just 1, so it's just TE to the minus T. This inverse is e to the minus T, e to the minus T. Okay, and of course over here we just have e to the minus AT here, or TE minus T e to the minus AT, or TE to the minus T. Alright, so if you remember, if you've actually done your integrals before, or your solving of ODEs, you notice that these are actually part of the particular solution, if I'm not wrong. Okay, these are part of your particular solution. Okay, if I'm not wrong, yeah. So that's one part. So we'll just have to deal with the rest of this part as well. So bear with me for a little while more. I'm just going to do the inverse Laplace of the first term. So what's the first term? Inverse Laplace. Okay, I'll have okay, let me get that out. The math cal L times whatever's in the bracket. So I have a fraction of b s over s squared plus omega squared. Okay, so and then we'll have a c as well. We have a c as well over here. Okay, what else do we have? We have two more terms. One is the d term, d over s plus 1, and e over s plus 1 squared. Now, of course, now it's a spilling of the page, so that's not too good. Let's move it to a new line. Okay, there we go. Oh, doesn't quite work. All right, because the brackets are not working. All right, so let's try again. Okay, so I just brought the other term down. Okay, and we'll have to inverse Laplace. We don't Laplace all of this. It's already in Laplace mode. So this is just to give you an idea. I'm not going to provide the full solution for you. But okay, let's see. What's s over s squared plus omega squared? This is actually, we'll have to look. Where's our sine and cosine? Okay, sine is omega. And cosines are with s, if I'm not wrong. Yeah, s over s squared plus omega squared. That's cosine. So that's b cosine omega t. So I'll take that out. And I'll put it at the bottom. Plus b cos omega t. So that's the first one. The second one will be to do with sine. Okay, so we'll have so we'll just take it out and we'll have fraction c over omega. Okay, because we have to so-called get this term to be in the form of omega over s squared plus omega squared. So if you want to do that, you want to factorize c out and you multiply omega on top, you have to divide the bottom by omega as well. So I go through that very quickly. Sine c over omega sine omega t. Okay, so I will just delete this other term here. And then of course d and e are very straightforward, right? D is d, okay, you have e to the minus at, or e to the minus t, in fact. Okay, de to the minus t, and I'll need to plus it here, of course. And then we'll just have the Laplace of e. So e, this one is just e times te minus t. T e minus t. And this is the solution to the ODE that we have. Okay, where all our terms E, D, B, C are all over here. Okay, I'm not going to simplify. I'm going to leave it as it is. Okay, because why? What I want to show you is just an example of how to solve ODE with Laplace transform. Now this is a second order ODE. Okay, so I still have one more example. Okay, so we did a second order. It's pretty complicated. Then let's do the first order. Okay, this is example 2. Okay, what's this ODE? Y prime plus 3y equals exponential minus 2t plus 4. Okay, so we'll do a first order ODE, example 2. We have a first order ODE. Alright, so again, this one should be quite quick. If you take Laplace transform of both sides, we'll have s f y of s minus y at t equals to 0. Alright, so these are your boundary conditions. So 3y becomes what? 3y of s. And what does exponential become? Exponential minus 2t becomes 1 over s plus 2. Okay, Laplace transform of 4 is just 4 times the Laplace transform of 1. What's Laplace transform of 1? That should be 1 over s if I'm not wrong. Yeah, Laplace transform of 1 is just 1 over s. Okay, so you have 1 over s. Okay, we can see that this is a lot faster than maybe the integrating factor if you don't like those sort of integrals. So again, I'll just bring this t equals 0 to the right hand side. And then what do you happen? What happens here? So we can just factorize y of s out. and just multiply, divide throughout by s plus 3. Okay, so I'll have this s plus 3, okay, and then we can just partial fraction it. Okay, fraction 1 over s plus 3, and then fraction 1 over s plus 3, and then the last one also has fraction 1 over s plus 3. Okay, you see that the solution comes about pretty quickly if you use Laplace transform for time-varying ODE, initial value problem. Okay, so let's do a y of t. Let's get back our y of t. So we'll just take inverse Laplace of all of this. Math cal L to the minus 1, left bracket, and we'll have a right bracket here. So we'll take a inverse Laplace. Okay, the initial condition one is pretty simple. This is actually just what? Okay, exponential minus 3t, exponential minus 3t. Okay, exponent. Oh. Okay, I might use yeah, different forms, and these two I'll probably have to partial fraction them. So I will just use Wolfram for a while. Okay, so the Wolfram partial fraction for the first one. Okay, for the first one, fraction. Okay, this is equals to, let's see, Wolfram. Okay, 1 over x plus 2 minus 1 over x plus 3. So that's very simple. Okay, 1 over s plus 2 plus 1 over s plus 3. Now this one, did I go wrong somewhere? Yeah, I did. There you go. And then there needs to be a minus sign here. Okay, so that Laplace transform is also quite easy. So we'll just substitute all of this in here. Alright, and we'll just get these two exponentials out. So what? I have to plus exponential minus 2t minus exponential minus 3t. Okay, so these two are out. Okay, so one last one is this. So I'll just Wolfram this as well. So I can just type partial fraction 1 over x plus 3, which is basically 1 over s as well, if x equals to s. So now this one also quite simple, 1 over 3x, 1 over 3x plus 3. So very simple. Okay, fraction 1 over 3s, and what? You have to minus 1 over 3, 1 over 3 s plus 3. If I'm not wrong, yeah, 3x plus 3. So okay, that's quite simple as well. All we have to do, this 1 over inverse Laplace of 1 over s is just it gives you back 1, so you have t over there. Oh no, not t, you have 1/3. Fraction 1 over 3, and then what? You have 1 over 3 e to the minus 3t. Okay, so if you want to simplify a little bit more, simplify this a little bit more, let's just collect some terms together. You have y at t equals 0 minus 1 here, because you want to collect all the exponential 3 minus 3t terms together. Okay, and then this minus 1/3 will go in, and that will become 4/3. Okay, so let's do fraction 4 over 3. Okay, maybe you can check Wolfram to see whether I did my math right. Okay. Okay, so this is the analytical solution of this ODE. How long did I take? Okay, so it's about 3 to 4 minutes to solve it through inverse Laplace. However, of course, I did use Wolfram to do these partial fractions. So that's kind of the only work you need to do if you don't want to like integrate directly this sort of equation here. So not too bad. Okay, so that's all I have. For the time being, we just went through how to solve ODEs using. We solved 2 ODEs using Laplace transforms. So again, if there are any, so I think that's it. I'm not going to talk anymore. Okay, thanks for watching. See you again. Bye bye.